Угу. Так, тут какая-то кнопка еще должна быть. Куда тут нажать? Тут красная горит.
Угу.
Значит, как включено, да?
Все, я запустил.
Okay. Well, today we are going to discuss some particular case of deformations, but which with terms contained in some holomorphic tangent bundle. So I'm going to first give some notations which are going to be often used, definitions and some assumptions. At first, a formal deformation is a multiplicative law which is written this way. In our case, we are going to consider omega bar is B-differential and what is most important holomorphic operator. So it's constructed from vector fields of type 1, 0.
Omega bar.
Omega bar, yes. For all I, yes. Constructed from vector fields of type 1, 0. Actually, the paper which I chose to discuss contains a more generalized conception of Lie algebroids, and when we study operators with vector fields from some some distributions of our manifold, yes, during the whole talk, M is a symplectic and complex manifold. Considering this product, yes, I forgot the most important variable h bar. So we're dealing with an algebra over power series in h bar.
H bar to the power I, I believe.
What?
H bar to the power I.
Yes, of course, sure. So we're going to, and most importantly, we're going to discuss the sections and connections on the following bundle. Let P be a symplectic frames. In other words, it is a principal SP bundle, but we are going to discuss the so-called while bundle which looks this way. This algebra with a hat is some kind of expansion of an algebra over power series. This one.
So I believe M is symplectic and complex, and overall omega, the symplectic structure, is
Yes. Of course, yes. That was meant. Omega is holomorphic.
So all coefficients are omega.
And yes, all coefficients and the coefficients in this formal deformation are also holomorphic. So this is our subject of discussion. So we're going to work with this bundle and study its sections and connections, mostly Fedosov connection and curvatures. With those, we are going to classify our deformations, which is also a beautiful result. So, as I have already said, we are going to set these operators be holomorphic, and in most of our theorems, we are going to set this important statement. We are going to set this map as an inclusion.
So you should define this
This is needed to.
But what is the right hand side? Did you give the definition?
Yes, this is a sheaf of holomorphic functions.
So does everybody know what is the sheaf of homomorph?
Well, in my talk, I wasn't going to speak a lot about sheaves, but in this case, we may consider it as some local holomorphic sections on our manifold, which agree with other coverings of our manifold, so-called gluing conditions. But we're not going to discuss sheaves a lot. They will be needed in several statements. Well, so all things also, we will also need this one, this construction. I think I can remove some writings from the board. So we're going to discuss another object. So let's p times let it be our file bundle. So as it is a bundle, we would like to have a connection on it. So definition. Fidos of connection, which is most importantly flat. And written this way. So nabla f equals z bar plus nabla 0. This connection comes from tangent bundle. And we also need two types of components. So this one is holomorphic type. And this one is anti-holomorphic one.
Probably you should explain what means holomorphic and anti-holomorphic.
Sure.
A short regression if I were you.
Of course.
So can you explain this? Because I don't think that everybody here is familiar with the notion of complex geometry.
Okay. Let's discuss it briefly. Since we have, when we have smooth case, we have differential forms with some sort of basis like this. When we have complex structure, we actually have a splitting of our even dimensional space into two halves, one of which is called holomorphic.
First of all, I think you need to complexify your tangent.
Yes.
So first of all, consider tangent bundle of a complex manifold and complexify it.
Yes.
You allow complex coefficients.
So our basis is split into two halves, which.
After this, you can do this.
Yes. By complexifying, we mean adding complex structure, which is an operator whose square is minus identity, and on one half it sends it onto another half, and the second half is sent onto the first one with the minus sign. So this is.
So it's an operator of multiplication by square root of -1.
Yes, of course. If from the definition, it follows from the definition. So when we have this splitting of our basis, let it be a tangent basis or cotangent if we discuss differential covectors. So we're going to, so this can be extended just as in a smooth case to differential forms which have, for example, P an order of holomorphic part and Q anti-holomorphic. So it can be written somehow like this.
cut the long story short, you can do the following trick. If x1 to x1, x2, and so on, x2n are coordinates, real coordinates, right? And you can actually form complex coordinates from them by just considering formal combinations of xi plus square root of minus 1y, right?
Sure, yes.
So z will actually be, zi will be xi plus square root of minus 1yi. So dz is like this, but dz bar will be xi minus square root of minus 1 dy, right?
Yes. Well, and just like in smooth case, we can introduce differential forms, which are sections of cotangent bundle of exterior product of cotangent bundle. So our in our setting we have some kind of forms which have two upper indices. The first one means holomorphic part, and the second one means anti-holomorphic part. And in this case, this one means the first part, and the part I have already removed is anti-holomorphic part.
So, just wonder whether everyone understands this. If not, let me just show it.
Sorry, can I ask a stupid question? How is tangent bundle is defined in the complex case?
The complex case it just
I don't want to go too long. So I think it is enough to do the following thing. So first of all, do you understand this? So now, wire bundle in real case used to have sections of the following form: sums, formal sums over k, and alpha a k alpha h to the power k of x y to the power alpha, right? So when we considered differential forms with coefficients in wire bundle, we had to add d x I to the indices, right? Is this clear?
When we consider what?
Differential forms with coefficients in Weil bundle.
Oh, right.
We used to consider it. Then, so I is Marx index. Then, in complex case, you will have to replace dxi to an expression like this, of this sort, right? Now, what is why is it now philosophy connection had the form the usual symplectic connection plus the correction term, which we used to write in the form, well, up to some coefficient, which I remember was like square root of minus 1 raised by h. Omega was the symplectic form, right? Symplectic form where we actually changed one of the coordinates, one of the differentials by non-commutative coordinates in Weil bundle. So there was one special term first, which we fixed. But after this, we added some differential one form of this sort, and our connection. So in these terms, our connection look like a joint action of this element plus a joint action of this element. Right? A joint action of some differential form on some other differential form is just a commutator of zeta and alpha.
It's a commutator.
Well, this is differential form with coefficients in Weyl algebra, and alpha is also differential form with coefficients in Weyl algebra. So when you have two differential forms with coefficients in an algebra, you can take their commutator in the sense of this algebra. Just take their product, pointwise product, and in both directions, in both orders, and take the difference of these two products, right? That's what you usually do.
So then where the non-commutativity comes from?
Weyl algebra is non-commutative. Weyl algebra.
AK is not commutative, right?
Yeah, AK is non-commutative. So Weyl algebra bundle is non-commutative. Now, this is the joint action, and what they do, what Gleb actually does, he splits this part here into 1-0 form and 0-1 form, according to the number of differentials, holomorphic and anti-holomorphic differentials which appear in the end of this expression. That's all what is done, nothing else. The way these coefficients, these coordinates appear, actually you can find it in any textbook on complex geometry. I don't think it's really very important here. You can imagine that your manifold is locally just Cn. So when you have Cn, you have complex coordinates. There is no problem with defining these differential forms.
I just wondered, why do we have to complexify?
We don't complexify. It's naturally complexified because we have complex manifold. Complex manifold means that we have complex coordinates, naturally. There are different ways to describe them in terms of real differential geometrical data. But for our purposes, it's enough to imagine that we have a space which is locally like an open subset in Cn. Then there is no problem with this definition in a naive way, of course. If you want to make it more accurate, you need to go all the depths into the definitions of complex bundles and complex geometry. But naively, you locally have coordinates z1 through zn, but you can also locally split them into x and y. z1, zi is equal to xi plus square root of minus 1 yi, locally. There is no problem. So then you also define z bar as xi minus square root of minus 1 yi. And then you get this. Why this is important is actually beyond the scope of our talk today. What is important is that in complex geometry there is one well-defined operator that is called the Delbour operator. And it is precisely the, how do we call this, Cauchy-Riemann operator in one-dimensional sense. It turns out that this operator is well defined. It doesn't depend on the choice of local charts in a complex holomorphic bundle. If you have a holomorphic bundle, you can define a connection in this holomorphic bundle. Try to define connection in holomorphic bundle. And it turns out that the first piece in this holomorphic connection, whatever you mean, not holomorphic, in this connection, can always be chosen in this way. At any connection on any bundle.
So what is just can you give me any description of this first operator?
D bar?
Yes.
Is just up to the sign which I always forget. It is d over dxi. So I think it's something like this.
X bar.
SI minus, I think, or plus, I don't remember. What is it, minus or plus? So you minus 1 d over dy, right? Is it like this?
Okay.
Plus or minus, I don't remember. It's Г.И.Шарыгin operator, just Г.И.Шарыгin, but I don't remember it's minus or plus. Do you remember this?
I don't remember the sign either.
Sorry?
I don't remember the sign either.
Signs are always my problem. I think it's plus rather than minus, in my opinion. It's rather plus than minus.
No, its square must be zero.
This is just operator on functions, as you see. It's well defined and bundle is so it's a sum over I, of course, and then we take d zi bar. So it's just the anti-holomorphic part of of the Ram differential.
I'm sorry, I can't see.
So dzi bar.
Why is it anti-holomorphic?
Sorry? Because we differentiate over the I bar and we use this here. So what is the Ram differential? In the usual sense, in the real sense, in the real case. It's just the sum d over dxi, right? Now we split the sum into d over dzi, plus d over dzi bar, dzi bar. So this anti-holomorphic part is this Bilbo operator.
And where is the holomorphic part?
It is not here. It is not part of the Bilbo operator. The Bilbo operator is just the anti-holomorphic part of.
I think we could write it in other coordinates. For example, just this, like d z bar e. I think this is a bit
Yeah, but also
shorter.
we don't use these. I don't remember this.
It depends on the coordinates. If we
No.
if we
I mean differential. So
use this and
No, I think we have to. Well, the Bilbo operator for me is just part of the anti-holomorphic part of
the
the
Ram.
Ram differential.
Yes.
So this is what we do. This is what we do. Right? So there are n holomorphic coordinates and n anti-holomorphic coordinates. So they just the way we rewrite these, if we use different coordinates, as just this. So this is anti-holomorphic part of the Ram, and it is well defined in holomorphic case, because when you change coordinates, the coordinate changes are holomorphic. So the anti-holomorphic part vanishes. So this holomorphic part and anti-holomorphic part of the Ram operators are well defined. There is no problem, there is no ambiguity. It doesn't depend on the choice of coordinates. So it turns out that when we have a holomorphic vector bundle, that is a vector bundle such that the change of coordinates from one coordinate chart of the vector bundle to another is holomorphic, then you can actually choose its connection in such a way that the anti-holomorphic part of this connection will just coincide with the Bilbo operator.
I can't understand. Is this part always vanishes when we have holomorphic bundle and?
So it vanishes when we change on the coordinate change functions.
Right.
So if you have a function which doesn't depend on anti-holomorphic coordinates, then it vanishes.
Mm-hmm.
But generic sections of a holomorphic bundle need not depend only on holomorphic coordinates. They can also depend on anti-holomorphic coordinates.
Okay.
Right? So generic sections do not depend. A change of when you change coordinates, So when you change coordinates from one coordinate system to another, you multiply your sections by some holomorphic matrix-level functions, locally defined, right? Since they are holomorphic, the bar applied to these functions vanish identically. And that's why we can actually choose the connection on any holomorphic vector bundle in such a way that the anti-holomorphic part of the connection will just coincide with d bar.
And everything else will
But this is also very important. This is remaining part of the connection, so to say, the holomorphic part of the connection. And this holomorphic part might be very complicated. We shall say that the connection is holomorphic if we can choose this holomorphic part in such a way that all coefficients, so all, actually all, how do you call this, all Christoffel symbols are here. So if we can choose these Christoffel symbols in such a way that they all depend only on holomorphic coordinates, then we are done. We have holomorphic connection on our holomorphic vector bundle. But it's not always the case. There exist holomorphic vector bundles which do not admit holomorphic connections. So you cannot choose a connection in such a way that its holomorphic part has only holomorphic coefficients. When I say holomorphic part, it means that it only contains partial derivations in holomorphic directions. But doesn't mean that all coefficients are holomorphic. They might not be holomorphic. You see? It's actually a very, it's not even crash course into complex geometry, the kind of explanation of the terms. Actually, complex geometry is a very large science, which I must admit I have very vague idea of. There are lots of delicate theorems in complex geometry which are worth studying. Now we only look into the very, very beginnings of this science, and our purpose is to find this kind of philosoph connection. So this is actually, this will stand for a symplectic connection. But in this symplectic connection we have chosen separately anti-holomorphic part and holomorphic part. So this is symplectic connection. And then we go for the correction term. And this correction term is again split into a holomorphic part and anti-holomorphic part. And it's done on purpose. It turns out that holomorphic part in some sense determines the anti-holomorphic part. That's actually what we're going to talk about.
Yes.
Yeah. Okay,
well,
that's my place. It's my seat. I'm sorry.
Okay. So since we're not only dealing with complex case, we're also dealing with Weil bundle. So just like in a smooth case, these components and also acquire some sort of grading. So A is equal to A minus 1 plus A 0 plus and so on, where so these terms are one forms, more concretely 1-0 forms. Well, I haven't written what does this mean. Yes, we have. It's some. We are dealing with some sort of formal power series with coefficients like this. And B requires the same decomposing, but we can notice that its indices start from 1 because, as it later will turn out, B is predefined by the previous terms of A. And well, I'm going. Well, the proof. I haven't written the theorem yet. So, since this connection is also flat by definition, we can, and it has some sort of decomposition.
What is G tilde?
So let me explain. So when you look at the Weil algebra, it is non-commutative algebra, right? Every non-commutative algebra can be regarded as a Lie algebra if you consider the Lie operation as, if you define the Lie operation in it as just a commutator of two elements, right? So Gi is a sub-algebra inside of this Lie algebra generated by terms of degree at least I in terms of variables yi. So Weil algebra has non-commutative variables y1 through 1 to n, right? So if you consider these elements, they give filtration. Everything which is determined by elements of degree not less than 2n is determined is called Gi. Gn. And you regard it as a Lie algebra, that's all.
So it's increasing.
Yeah, it's increasing. So actually the degree grows. I believe this is the definition. Is this true?
Yes, yes, sure.
I just don't remember which kind of filtration they actually use. But I believe that's what I would say.
Since we have splitting, since we have a complex case, we have those components of our curvature. The first one looks this. And this part is denoted by theta, and it lies in two zero differential forms with coefficients in formal power series in H bar. Well, we have also this component d bar A plus nabla 0b plus the commutator of A and B, which will be denoted by phi, which lies in forms type 1, 1 with same coefficients in formal power series in H bar. And the last one, which later will be turned out to be determined by this one, is d bar B plus half of this commutator, and this one will be denoted by tau from omega 0, 2 forms with coefficients like this. So we also have Bianchi identity. The theta plus phi plus tau equals to 0. So this actually these components define some class in cohomologies. Well, I was going to give a theorem, but since but its proof is rather complicated, so I will give some sort of sketch of a sketch of a proof.
So what kind of theorem do you have?
I'm sorry.
So yes.
Ah. Yes, these terms I shouldn't remove them yet. What was there? There was d bar, and here was d bar b. Since b was 0, 1 type, d bar actually with composing it with b actually 0, 2 part. In complex geometry, we may also think about some sort of rhombus, yes. And for example, here is 0, 0 type. Here we have 0, 1. Here 1, 0, and so on. Here we have 1, 1, 0, 2. And d bar actually moves in this direction. And so on. This rhombus is also called Hodge rhombus, but we're not going. We won't need it in our talk. So we need a theorem which actually helps us to classify our fields of connections. So the theorem is so I have already removed. So we have connection, then we have also a curvature of this connection. So we have this theorem, which helps us to classify our deformations. So let nabla and nabla prime be fields of connections. So if they have the same curvature class, I think I can clear this.
This is no holomorphic theorem. When you speak about this theorem about fields of connections, is it holomorphic or non-holomorphic theorem?
Well, this theorem it has some sort of smooth.
So let's begin with smooth version, which we actually
Yes, smooth version.
has been described.
Yes, I think it is worth noting. The first point where smooth case and complex case begin to differ. So in smooth case, in real case, if nabla and nabla prime are gauge equivalent, if the curvature classes coincide, if and if only, of course.
So what are the curvature class? If you explain it. Actually,
Oh.
when I talked about loss of quantization, let me make this brief digression again. There was a theorem which actually was the crucial part of the loss of theory. The theorem follows as follows. If you want to construct a philosoph connection, that is what philosoph himself calls a Abelian connection, you should begin with any symplectic connection, and then you add some correction term of the form square root of minus 1 divided by h plus omega y. That is the kind of non-commutative version of the symplectic structure, plus more correction term, right? That's what I began with. And then, with the help of this correction term, you can make the operated nabla square, sorry, d square, that's what it is, and d square applied to any alpha will look like a commutator of alpha with any given closed two-form on the manifold L. That was the real version of this theorem, right? So when we spoke about the loss of quantization of real symplectic manifold, I actually proved this theorem that for any closed two-form on M, we can find a correction term zeta such that this operator will be equal to the commutator of this form, and as phi is central, this will actually turn out to be 0. So this phi is we can regard this phi as the curvature, the actual curvature of Philosoph's connection, right? And the class of this phi in the second Durango homology of the manifold is a curvature class, precisely the class which Gleb is talking about, right? Now, this phi is more or less this sum of 3 elements. In real case, this phi was totally arbitrary. You could choose any closed element, closed two-form on M. Not just two-form, but actually formal power series of closed two forms on M, right? So phi was in omega 2 of M times formal variable in all degrees. So for any element, you could have such phi, and two quantizations would be equivalent if and only if these two phi's determine the same cohomology class. Now if you look here, this sum theta plus phi plus tau, it plays the role more or less of the same gradient of phi in real case. However, in this sum, not every element, not all elements are equal. Some of the elements are more important in complex case than the others. And that's precisely the purpose of this talk. It turns out that you cannot choose arbitrarily, freely, all three ingredients in this term, in this sum. You can only choose, I think, two of them.
The first two, yes.
The first and the second one. Even probably, yeah, the first and the second one. And then the third one will be determined automatically by these two elements. That's precisely the thing we need to talk about. That's the purpose of this talk.
Yes. So, as it was also said, in real case, this theorem would be like nabla and nabla prime are gauge equivalent if and only if the curvature classes coincide. But in complex case, gauge equivalence gauge equivalence needs to be not between nabla and nabla prime, but it can be we can add some sort of closed differential form to one of these terms. So if they are gauge equivalent, then and only then their curvature classes coincide. So I will give this row. So in this case, if and only if their curvature classes coincide. So the proof is a lot like the real one, and involves proceeding by induction over our gradient of algebra G.
So what is the exact phrasing of this theorem in complex case? Can you show what is the exact phrasing of this theorem? This is a theorem from the paper of Neston-Segan, right?
Yes.
Can you give the reference first, and then just write down the theorem explicitly from the paper? Because the theorem should be formulated very accurately.
Okay, let me write it again. Let nabla and nabla prime be two G-valued Fedosov connections. Then the curvature classes coincide. If and only if there exists one form alpha with values in formal power series of H bar. such that nabla and nabla prime plus alpha are gauge equivalent. So we can see that, unlike in real case, we admit here equivalence between not only between two connections, but also between connections plus some one form alpha with values in form of series in H bar.
So this is a central field. This alpha is actually central.
Yes.
So if you add this alpha, the connection will not change somehow.
The curvature will not change.
The curvature, curvature will not change.
Because it is also closed.
Yeah, closed. Right.
And the curvature will change by its differential. So if it's closed, then the curvature will not change at all. Well, I think the proof is going to take a lot of time because it is rather technical. But its idea is a lot like in smooth case by proceeding.
In smooth case, we could use some iterative procedure.
Yes, and
operation which we use mathematically, and it would converge to something unique. I think that it is not the case here. Or do they have some iterative process there? Do they have iterative process? I don't remember. I think they just work.
Yes, there is an iterative process here, but during this process we have. I can actually write down the proof, but I think we won't have enough time for other theorems. So I think that the main idea of this proof is
Is just one form or 0, 1 form?
it must be 0, 1, of course.
So 0, 1 form. We are free to choose the 0, 1 form. But if it were just one form, there would be no difference with smooth case at all.
Yes, because this form, because we have deformations along 1, 0 vector fields, because we have these deformations, and this form, since it is the type 0, 1, it is, as was already said, central.
But it's not central because it's type 0, 1. It's central because it has values in the center of wire algebras. But since it is 0, 1, you can actually add it without changing the class of your connection.
Yes. I'm going to give another theorem, but it involves actually our algebra. This one actually lies not only lies but coincides with the kernel of our Fedosov connection.
No, that's not the case. It's definitely not the case. I mean, it would not be the case. Because Fedosov connection, only flat part So the kernel of loss of connection is the flat sections. And flat sections, in a real case, coincide, they can be identified actually with functions
Yes,
on
we
the
need
base.
we need to restrict it.
Sorry, no. The kernel of loss of connection coincides with is isomorphic to the space of functions on the base,
Yes.
and not to the Weyl algebra at all. The space of functions on the base, they're actually, they're the kernel of loss of connection.
Yes. I need
But
to
not-
restrict this
Well,
connection.
the left-hand side is definitely not this. It cannot be in central. It cannot be isomorphic just to the Weyl algebra. I don't believe this. It should be, again, functions, homomorphic functions probably, should be isomorphic to the kernel of loss of connection. At least in smooth real case, kernel of loss of connection coincide with, well, not coincide, is isomorphic to the space of all functions on the base, on the manifold.
And here we have a restriction
To what?
to this.
Yeah, but never mind, it's just the same. Yeah, that's true.
Okay.
Good.
So
It's very strange. Can you give a reference? I don't remember.
it is from the same paper.
But I don't remember. Can you give a reference?
Uh,
Yeah, this paper with you. Take a look.
it is theorem 5.6.
You have this paper with you.
No.
Take a look. So, but what do you want to show?
Well, and I also wanted to state another theorem about local deformations. Because locally, just in local case is not it doesn't differ very much from the smooth case because locally all formal deformations are isomorphic to one deformation called Weyl deformation.
That's true. That's one,
Yes.
one of the properties which I also mentioned in the real case, in the smooth case. Locally, loss of deformation is isomorphic to Weyl algebra. Because locally, you can choose actually always you can choose W coordinates. In W coordinates, the loss of construction boils down just to Weyl product. So what was this theorem? 5 dot what?
5.6.
Let me take a look. Just to be that.
For the next theorem,
yeah, but that's different. They speak about sheaf.
yes, they discuss the sheaf of.
Oh, I see. That's because.
Yes, I.
So, and this definition, this A is a little bit different again. So, first of all, they speak about sheaf, not about the product.
Yes.
It's not isomorphism of algebras, it's isomorphism of sheaves. And it's precisely what you just mentioned. That locally,
Yes.
the kernel of this, yeah, that's precisely what you mentioned.
Yes, I must mention that this is not isomorphism of algebras.
I see. Now I see. That's precisely what makes me.
This is an isomorphism of sheaves.
Now I see. Yeah, sure.
So locally, the sections are of this algebra lies in the kernel of Fedosov connection. So I'm going to.
So that's precisely again when I made this digression. I think that I mentioned this when we talked about Fedosov quantization in real symplectic case. But one of the main properties of Fedosov quantization is that if you take Fedosov algebra, you remember Fedosov algebra. Sorry, just make this digression to make it clear. So you recall that Fedosov connection, Fedosov algebra, Fedosov construction was as follows. You have this Fedosov connection, Fedosov Weil algebra bundle, right? You have this flat connection on it, right? So star denotes just the degrees in the direction of differential forms, right? Then kernel of this Fedosov connection D would be on one hand isomorphic to the algebra of functions on the manifold with these coefficients, right? On the other hand, it will be a subalgebra inside WD. So this isomorphism Q induces the star product here, right? Now, if you take this WD, and one of the properties of Fedosov quantization was that locally, so for any point in manifold, there exists open set around this point, such that the restriction of WD to this open set will be isomorphic to Weil algebra. And that's more or less clear because locally every symplectic manifold admits double coordinates in which symplectic form has trivial standard type, right? So when you apply Fedosov construction to the standard symplectic, constant symplectic structure on R to N, you definitely will obtain Weil algebra, just Weil algebra. And that's precisely this isomorphism, local isomorphism, because again, these are local isomorphism. When we speak about sheaves, it means that we only restrict our attention to local properties on the right and on the left. So on the left we have sheaf of Weil algebras on Dabu charts, more or less. For every point we have a Dabu chart around this point, and we consider the Weil algebra at this chart. So on intersections we have more or less map from one to another, restriction and so on. That's more or less clear. On the right hand side we have the space of flat sections inside here. And every flat section we can restrict to a set and to subset, and that will give you a sheaf, right? And now we have this isomorphism. That's this.
Yes.
It's not the isomorphism of algebras. It's not isomorphism of global sections. It's just local isomorphism.
Yes, there is actually.
Sorry, when you said this, I didn't realize you were speaking about local properties.
Yes. Thank you. Well, I'm also going to write down another theorem. At first, as we already said, we have some sort of splitting And this splitting also extends to splitting on differential forms. And what is most important, it also admits splitting of cohomology groups. So if we take our de Rham cohomologies, we can split them this way. We need this well, the notation is maybe rather confusing, but actually it means rather simple thing, plus this. So this one are cohomology classes of type 1, 1 and 2, 0, and these are classes of type 2, 0. As was already said, actually this part will define the deformation, and this part is going to be defined by this one. So before it, I'm going
so
to.
What is F1? Did you explain this splitting?
So
F1
well,
is just the sum of 2, 0 and 1, 1 part, right?
yes, and everything which does not lie here lies here.
I think I know that if the manifold is Kählerian, and we have direct sum of 2, 0, 1, 1 and 0, 2 parts in cohomology. But I think this is a kind of additional assumption that we can have this splitting in cohomology.
Yes.
Because for generic complex manifolds, the splitting in differential forms does not entail the splitting in cohomology. In
But
Kählerian case, that is the case, but then they have splitting in all three.
but we have a symplectic form here. M is a symplectic manifold.
Symplectic form actually. So do you mean that the symplectic form
It
gives us this splitting addition, this additional splitting? I don't know.
something like that.
Okay, let's believe you. Let us believe you. I don't know, but that's possible. I'm not sure about it, but it's possible. So if your manifold is Kählerian condition, and in case you don't know, everybody, Kählerian condition is kind of additional assumption which you use for complex structure. And this assumption, although very natural, actually leads to lots of important consequences. One of these consequences is that cohomology, graph cohomology, splits into direct sum of all three terms of cohomology. Right?
Yes. So now we can, when we have this.
I'm sorry, I don't understand. What do you mean by what is the grading on cohomology? So you have splitting of differential forms.
We have this.
No, what do you mean when you write H02? What do you mean? It's
For example, this. Well, this means that well, we have splitting in cohomology, as just like in differential forms. We also can.
Again, the splitting in cohomology is an additional assumption. In case you know what,
I don't understand.
so in case you know what are sheaf cohomology, then you can think about these terms, about these summands in this splitting as sheaf cohomology. 0, 2, 2, 0, and 1, 1 parts in differential forms are three well-defined sheaves on manifold. Right? Now I can consider its sheaf cohomology in all these three directions. I will give you nice three groups. If you don't know what a sheaf cohomology, then you should probably think about the Bilbao operator, d bar. D bar only increases, I think, the second part.
Yes.
The second index. D bar square is equal to 0. So since d bar preserves bi-gradient somehow, I mean it preserves the splitting of gradients into two parts, only acts in one direction. It determines cohomology of this sort. So in this case you can consider this as d bar cohomology of corresponding sheaves. With corresponding coefficients. Is this clear?
Mm-hmm.
Well, let's recall we have curvature class, which looked like this: theta plus phi plus tau, and actually, for example, theta and phi, let's denote them by alpha, and tau actually lies here, and alpha lies here. And so the theorem is given by the same authors who gave this theorem. So if we have this part of our cohomology class so it looks like this: 1 by EH bar plus omega plus and it is also with coefficients in H bar. So we have something like cohomology classes with coefficients in formal power series, and we also can think about it as a power series with coefficients in cohomology classes of our manifold M, like from this, from there. Oh, and the theorem states that there exists a unique tau from H to 0, 0 to homology group with also with coefficient in formal power series, such that alpha plus theta is would it be correct if I call the curvature class the characteristic class, or it is not the same?
Sorry?
If I write here a character class of
What class?
we have in this theorem we also have already have a Fedosov connection. I have forgotten to write this, and this splitting. And also we have a Fedosov connection. I have forgot to write it somewhere, but the theorem states that if we have a Fedosov connection with splitting and we have alpha, which lies here, there is a unique cohomology class from H to H02 lies with coefficients in formal power series. So, no. We have a Fedosov connection splitting and this element, then there exists unique cohomology class from here.
I don't think we have a Fedosov connection. I think, suppose we have splitting and we have a class alpha in this cohomology. Then there exists a unique class tau
Yes.
in H02.
Such that alpha plus tau is a characteristic class.
Curvature class of Fedosov connection.
Yes, curvature class.
Fedosov connection corresponding to holomorphic. Corresponding to the holomorphic star product. So if you just consider any star product, you see the problem is that if you consider any star product, then
Yes, actually.
you can choose any class in second cohomology. But if you restrict your attention to holomorphic star product, then there is a restriction. You can only choose freely the first class, alpha, and then tau is determined uniquely.
Yes.
That's precisely the subject, the improved.
So we cannot just freely, we can just arbitrarily choose homology class from here, but we need to choose a class from here, and this class will actually define, will classify our connections, and it will define the class from H02.
Okay.
Well, the proof, just like the proof I didn't give here, bases on iterative process, and I would like to give the theorem which uses this theorem and this theorem.
So we are going to conclude with a corollary of these two results.
Yes, I would like to give the conclusion.
The corollary.
Yes. So, since we have this condition, and then we have this theorem. So, the set of isomorphisms classes of formal deformations just like I have said, it depends only on this part, so it is in bijective correspondence.
That's a formal deformation, a formal holomorphic deformation. I think. You are missing this point.
Yes.
Because it's not just any deformation you need to become holomorphic. So
Yes.
when you say T is 1, 0, it means that these bidifferential operators only have holomorphic partial derivations. Again, when you have Z1 through Zn, coordinates and z1 bar is the n bar coordinates, you can consider d over dzi and d over dzi bar. In general, your bidifferential operators will contain both types of partial derivations. But when you take d over dzi bar, if you take them, then, well, in the presence of holomorphic functions, they will vanish. Right, and also I think it's not just T10 deformation, but you also need holomorphic coefficients in the deformations, right?
Yes, of course.
When you have T10 deformations with holomorphic T10
Yes,
deformations.
let's just note that the
So
formal.
holomorphic deformation. That's actually really very important.
Yes, if we have if we have derivatives
So you don't
For
have
along-
directions in directions of d over d in anti-holomorphic directions, but that's more or less clear because when you apply them to holomorphic functions, they just vanish.
yes.
But you also cannot have coefficients with anti-holomorphic coordinates in them. So actually you have to eradicate both partial derivations in anti-holomorphic directions and coefficients with anti-holomorphic coefficients there. Okay.
Okay, so these classes are in correspondence with this group. Actually, with elements of this element. So if we have alpha, we can also write it this way.
I think we've forgotten the symplectic form.
Yes.
The first term will be symplectic form.
Yes, the first term has it. Plus alpha 1 h bar plus alpha 2 h bar squared and so on. So if we have this element which lies here, we have a family of these maps. Actually, it just means that no, it was a small mistake. We have maps which takes n minus 1 previous alphas and send them in the second cohomologic group here. So we have this note that this is tau n. It is not tau itself, it is its coefficient. So the curvature class given this expression, our curvature class is given this. or probably actually if I write it, actually this means just this one plus tau, which lies here.
Is this all? I think it is.
Yes. For example, if we have, we have two formal deformations, such that for some n, alpha n equals to alpha n prime, but tau n is not equal tau n prime, then there exists k lower than n, where alpha k is not equal to alpha k.
That's the corollary, yeah?
Yes, this is a corollary, probably to clarify this strange formula.
I think this is the purpose. This formula is not strange. It only means that when we said that the last term in this curvature class is determined by the two previous terms, that tau is determined by
Not only two previous.
phi and theta, it actually meant that at every stage, Tn only depends on previously chosen alphas, phi and theta.
Yes.
So there is no, it doesn't depend on all the terms. It only depends on what you have already chosen.
Yes, because the proof which stated this used induction, and the tau is constructed with knowing while knowing the previous terms of by knowing the lower terms of alpha and or theta and phi.
Okay.
And also, no, well, this is just a small corollary. Well, probably that's all.
Okay.
Thank
you. Are there any questions?
You forgot to add the condition to the zero.
Yeah, of course.
That is cohomology groups maps subjectively.
This was an assumption I made.
From the very beginning.
Yes, in the beginning, because it was in every theorem as a statement. I decided to put it in the beginning, not to replicate it more than once.
The cohomology maps from H to M, from H1 M C and H2 M C to H I M or M subjective.
So when you do
Cohomology is
the Randall cohomology maps subjectively to the shift cohomology. But that's more or less what we said about this splitting.
yeah. But I missed this part of your talk, and that is why.
Yeah, but that's assumption is technical.
Yeah.
Nobody actually paid good attention to it. And it was
But this is important.
it's important, yeah, definitely, sure. Otherwise, we shall not have this splitting. We shall not have this all this. But it is technical. It's an important technical assumption. I think
some important technical assumptions imply the emptiness
yeah,
of the
precisely.
set of considerations.
But yeah, but Keller case is already.
Yeah.
Keller case is something we can take our attention just to Keller. And that will be perfectly fine. Okay, I think it's time. There are no questions.
I have a question. Is there any explicit formula for these tau?
That's precisely the question, which I think is still open, in spite of the fact that this construction has been around since 1999. The paper was published about 1999 in the archive, and it was later appeared in printed form. So it's already more than 20 years. This theory exists for more than 20 years, but no explicit formulas, universal formulas for all those tau are known.
Yes.
There's a conjecture, which probably, at least I haven't heard, probably in recent say 3 or 4 years, they appear because I didn't pay attention to this subject in this last few years. But before that, it was still open. There's a conjecture that these maps tau coincide or somehow related with so-called Rojansky-Witten invariants, which are constructed with the help of very similar classes. Actually, if there exists, well, actually it's clear that if there exists in holomorphic connection in the usual sense, that is connection with holomorphic coefficients. Yeah, if there exists holomorphic connection, then no such theory is needed. We could just use this holomorphic connection, just like Fedosov did with in smooth case. And in this way we would obtain holomorphic star product. Just this iterative process, when it is applied to holomorphic initial data, it produces holomorphic star product. Right? There is a very nice cohomological construction called Atiyah class, which actually is an abstraction for the existence of holomorphic connection. It's a cohomology class in some fancy kind of sheaf cohomology. Right? So there is a on the other hand, so if this Atiyah class vanishes, then there exists a holomorphic connection, and all taus can be taken just zeros. There's no problem. All taus vanish. Right? Now there is so these taus they should depend somehow on Atiyah class. On the other hand, there is this construction. There is a construction of this so-called Rojansky-Witten invariants, which are also based on the extensive use of Atiyah class. So there is an assumption, which I heard of, and I don't know the current state of art in this direction. Well, a few years ago it was still open, that there is a relation between with this Rojansky-Witten invariants and tau classes of Nernst-Sigma. I think it's still open. I haven't heard it's been closed. It's been somehow explained. It means that this is actually a very hard problem. So even given some small insight into it would be, I think, a good thing to do. So if somebody is interested in this, you are welcome to call on to me and discuss this somehow. Okay. If there are no other questions, we can stop here. Sasha, can you please check the chat now? So no, there is no question. So let's think that we are done with this.
Так.
Okay.
Так. Так.
Goodbye. I'm closing the conference.
Goodbye.
Okay.
Ничего не ответил?
Нет.
Я боюсь, не помню.
Так, вот эта штука, она куда-то нажимается?
Нет, просто там, правда, там сам
Так, куда тут нажимать? Если еще более сложный.
Я не знаю, что это.
Тут, если что, есть кнопка mute, в общем-то.
задають?